The underwater world, a fabled arena for explorers and adventurers, home to strange and beautiful creatures dwelling among coral reefs and kelp forests. Today, with proper training and a thorough understanding of the underwater environment, men, women, young and old alike can comfortably venture beneath the surface.
This video is the first in a 4-part series designed to complement your Naui scuba course and to supplement the other educational materials you'll receive.
It's important to understand the many changes a diver will experience and why they occur. In this program, we'll discuss how the water environment differs from air.
We'll define pressure, and we'll examine how pressure directly affects us when we submerge.
The most significant difference between air and water is that water is heavier. Compare a cubic foot of water to a cubic foot of air. Seawater weighs 64 pounds, while air weighs about 0.08 of a pound. This difference tells us that water is more dense by about 800 times. Fresh water, without the added salts and minerals found in the ocean, weighs 62.4 pounds. Divers quickly discover that the density of water affects our senses of sight, sound, and touch.
One of the most obvious changes is how things look. Underwater, objects appear larger and closer than they truly are. This effect is called refraction, and it's caused by the bending of light rays as they travel through water and air. Until you begin to compensate for the apparent distance of things, it's common to reach out for an ascent line, for example, to find that you've just missed. After you've been diving a while, you'll realize the huge fish you saw may not have been as large as you imagined. Color is affected underwater as well. Sunlight is really a spectrum of colors that we can easily see in a rainbow or prism. Each color dissipates as light travels through water, an effect called absorption. Red light goes first. Next is orange, then yellow, until even in clear tropical waters, only green and blue light remains. An underwater light restores the brilliant colors of marine life.
Diving is a visual sport for most of us, and we focus our attention on what we see, often ignoring what we touch. Sometimes divers surface before discovering they've received a minor cut or scrape. The underwater world is a noisy place. Loud snaps, grunts, and pops emanate from fish and invertebrates. And the noise from each exhalation fills a diver's ears. In air, we locate the source of a sound by determining which ear received the sound first. Sound travels approximately 4 times faster through water than air. Underwater, the time differential is too slight to be detected. The sound of a boat propeller is easily recognizable, but it's difficult to identify where it is.
Anyone who has jumped into water with a temperature of 65 degrees remembers the unpleasant shock. Yet wearing only a bathing suit, 65-degree air remains comfortable for quite some time. Water conducts heat 25 times more efficiently than air, removing heat from your body faster than you can produce it. Divers who are uncomfortably cold experience a diminished ability to think. They use air faster and can become fatigued. They also lose manual dexterity and may experience difficulty handling their equipment. Divers who are cold should exit the water to warm up. Prolonged exposure to cold can result in hypothermia, a life-threatening condition. Exposure suits, like wetsuits and dry suits, are necessary to control heat loss. Different types of suits are used in waters of different temperatures. Even in the tropics, some protection is necessary for extended exposures. Suiting up on warm days can trap heat inside the exposure suit. Overheating can result in dehydration and exhaustion, so it's a good idea to cool off if you begin to feel too warm.
Water exerts a buoyant effect on our bodies and the equipment we wear, allowing us to hover at any depth, feeling weightless. This buoyancy acting on an object is equal to the weight of the water the object displaces. So, a 1 cubic foot object that weighs 64 pounds and displaces 64 pounds of seawater will neither sink nor float. This state of suspension we call neutral buoyancy. An object of the same size that weighs less than 64 pounds is buoyed up by the water and will float, which we call positive buoyancy. And a 1 cubic foot object that weighs more than 64 pounds will sink, which we call negative buoyancy. Each diver has his or her own buoyancy characteristics, depending upon size, proportions of bone, muscle, and fat, and the equipment worn. Let's see how buoyancy changes underwater. A wetsuit is made of flexible rubber that traps thousands of small bubbles. It floats and requires added weight to counteract its buoyancy. On descent, the bubbles compress, the volume of the suit decreases, and it becomes less buoyant. Divers add air to the BC to compensate for this compression and maintain neutral buoyancy. At the surface, an inflated BC allows us to float. To descend, air is vented from the BC so we can swim toward the reef below.
Weight belts are used to counteract the inherent buoyancy of exposure suits and the individual diver. Use only enough ballast to allow a descent from the surface. The scuba cylinder also undergoes buoyancy changes during a dive. Air has weight. As we consume the air, the tank weighs less, and its buoyancy increases. Breathing normally underwater results in a slight up and down movement as the amount of air in the lungs changes. A relaxed, comfortable breathing pattern makes buoyancy control easy. Diving neutrally buoyant increases our enjoyment of the underwater world. It also helps ensure divers don't touch and damage delicate marine life dwelling along the rocks and reefs.
So far, we've discussed some of the sensory and physical differences we encounter in the underwater environment. But there are also effects resulting from the weight of air and water called pressure. The atmosphere that surrounds the Earth has weight. If we measure a 1-inch square area at sea level, the Earth's atmosphere weighs 14.7 pounds per square inch, or psi. We also call this 1 atmosphere, or ATM, of pressure. Because fresh water is very dense compared to air, a 1-inch square column only 34 feet high also exerts 14.7 psi, or 1 ATM of pressure. It takes 33 feet of seawater, with dissolved salts and minerals, to equal 1 atmosphere of pressure. We talk about pressure in 2 ways, absolute and gauge. Absolute pressure includes the weight of the atmosphere above. So at 33 feet, we find 2 ATMs. Gauge pressure ignores the weight of the air above. So at 33 feet, we have 1 atmosphere. At 66 feet, we have an absolute pressure of 3 ATM and a gauge pressure of 2 ATM. A pressure gauge measures pressure in the tank compared to surface pressure. so it reads 0 until the tank is turned on. Changes in pressure affect the volume of air in a flexible container, like a balloon or your lungs. As ambient pressure increases, the volume of air decreases. At the same time, the density of air in the container increases as molecules of air are squeezed closer together. When we take a breath and submerge, the air in our lungs is compressed. As we ascend, volume and density return to normal. On scuba, the air we breathe from our tank is at ambient pressure. As we dive deeper, our air consumption rate increases. Lung volume remains consistent with each breath. However, the density of the air increases with depth. The deeper we go, the more molecules of air each breath holds, and the faster we consume the air in the scuba tank.
The changes in volume caused by pressure affect a diver's air spaces, such as ears, sinuses, lungs, and face mask. The air in these spaces compresses with descent and can result in an uncomfortable side effect called a squeeze. An ear squeeze results when water pressure pushes on the eardrum upon descent. This can be painful, and if ignored, can result in a ruptured eardrum with potential loss of hearing. The solution is simple. Pinch your nose and blow gently against your closed nostrils. Air travels through the eustachian tube from the throat into the middle ear, balancing or equalizing the pressure in your ears. We should equalize early and often. Start just below the surface and continue every few feet on your descent. If you have difficulty equalizing, stop, ascend a few feet, and try again. Equalization can also be accomplished by wiggling the jaw, yawning, or swallowing. Find the method that works best for you. Sinuses are equalized as you equalize your ears. However, a cold or allergies can cause inflammation that blocks sinus passages. Don't dive when congested. On descent, increased pressure compresses the mask against your face. Simply exhale through your nose to equalize. The air in our lungs compresses and expands as we go down or up. By breathing continually, we are, in effect, equalizing our lungs all the time. If we hold our breath, however, expanding air in our lungs can result in an overexpansion injury. The result is ruptured lung tissue, which can allow air bubbles into the bloodstream or tissue spaces around lungs. Bubbles can block blood flow. This is called an air embolism. In the brain, this can produce stroke-like symptoms. Overexpansion injuries can be avoided by following a simple rule. Breathe continually. Never hold your breath.
The underwater environment changes how we see, feel, hear, and move. The density of water has a buoyant effect that we can control to hover effortlessly.
And water exerts pressure that divers must compensate for to prevent the effects of squeezes or overexpansion. Understanding the properties of air and water and learning how to control buoyancy are keys to becoming a good diver.